Alright, so today we want to discuss what we call periodic trends. So periodic trends are patterns of characteristics that we see across the periodic table. So periodic trends are related to the periodic law. So the periodic law states that when you arrange elements in order of increasing atomic number, that they fall into regular patterns. Okay, so we know that families or groups on the periodic table react very similarly. We know that all the group 1A elements form a +1 charge, so they react in a similar fashion. So this is somewhat an extension of that. There are also other patterns that occur as you go across the periodic table, or as you go up and to the right across the periodic table. And that's what we're going to discuss today. Those patterns we'll call periodic trends. So there are 4 major periodic trends that we'll discuss in this class. There are a couple others that you'll discuss in either AP or IB or college level chemistry, but we'll stick with 4 for the sake of this class. So the first trend we'll discuss is atomic radius. Okay, so a formal definition of atomic radius is half the distance between the nuclei of neighboring atoms. And so if we think about what that means, you have an atom, you have another atom, okay, the distance between them, okay, if you divided that in half, you would have the radius of that circle. If you thought about an atom as a circle, it's not really a flat circle, that's one way to think about it. So that's the formal definition. A more colloquial way of saying atomic radius is how big an atom is. Okay. We won't really use these trends or patterns to quantify the size of these atoms. We'll just compare which one is larger than another one. So it's perfectly okay to think about atomic radius as how big an atom is. So if I ask you which is larger, chlorine and bromine, you think about the atomic radius trend. So what we're going to do for each of these trends is we'll define it, I'll tell you the pattern across the periodic table, then I'll explain to you why we have that pattern, or why we see that pattern, okay? So I'll abbreviate these. Atomic radius increases as you move down a column, or I can say a group, and as you move left across a period. Okay. So there's several ways to word that. I can say atomic radius increases as you move down and decreases as you move right. Okay, so every how you want to learn that, I typically say or state the trends in terms of increasing. Okay. So the radius increases as you move down and increases as you move left. Okay. So I also want to make a note. Okay. So atomic radius increases far more as you move down. Okay. So we'll say as compared to moving left. Okay. So as you move left, you increase, but you increase far more as you move down a group. So let's go ahead and explore this trend. Let's see why this is in fact the case. So we know that the nucleus of an atom is very tightly packed together. So the nucleus of different atoms, or the nuclei of different atoms, does vary slightly in size, but that doesn't affect the overall size of the atom. The size of the atom is determined by the location of the electrons. So electrons determine the size of an atom. So let's look at the downward trend first. So if we were to go down the periodic table, so from period 2 to period 3, what do we correlate period number with? And hopefully you know we correlate period number with number of energy levels. So if I look at period 1, okay, so that would be hydrogen and helium, versus period 2, versus period 3, so hydrogen versus lithium versus sodium, period 1 only has 1 energy level. Period 2 has 2 energy levels. Period 3 has 3 energy levels. Okay, so hopefully this will be pretty easy, okay, to explain why as you go down the periodic table you get larger atoms, okay, because you add energy levels. So that's the easier of the two explanations here. Now let's think about as you go from left to right. So let's just look at, let's say period 4, okay, potassium and calcium. So potassium and calcium both have how many energy levels? So they're on period 4, but they have 4 energy levels. So that doesn't help us. But let's look at their nuclei. So potassium's nucleus, okay, so we're at K versus Ca. So potassium's nucleus has a plus 19 charge. Now the atom doesn't have a plus 19 charge, but the nucleus does, because the nucleus is only the protons and neutrons. So if there are 19 protons in potassium's nucleus, it has a plus 19 charge. So calcium's nucleus has a plus 20 charge. Okay, so we have a symbol that we use to describe this, a capital Z. Okay, we use that to describe nuclear charge. Okay, so Z for potassium is 19. Z for calcium is 20. We don't have to say plus 19 or plus 20 because nuclear charge is always positive here. So now let's think about these electrons now. I'm not going to draw the first 3 energy levels. I'm only going to draw the 4th energy level. So just pretend there are 3 below this. So I have these electrons around it. Okay. So what do you think would be able, and these aren't drawn to scale, I apologize. So what do you think would be able to pull electrons in closer? A plus 19 charge or a plus 20 charge? Yeah, a plus 20 charge. So the greater the nuclear charge, the closer they can pull electrons in. Okay, so we'll say the greater the Z, the closer electrons can be held. Okay, so if you can pull electrons in closer, that means you get a smaller atom. Okay, so as you move right across a row, you get smaller atoms because the electrons are being pulled in closer. They're being pulled more tightly. So as you move to the left, notice the atomic numbers decrease. So the electrons aren't being held as tightly, so the atom is slightly larger. So you might be thinking, well, in the previous example, you went from lithium to sodium. You went from 3 protons, a Z of 3, to a Z of 11. Shouldn't 11 pull in closer? Well, that's a valid thought. But the addition of a whole new energy level makes the atom so much larger it negates any effect. Okay? So hopefully you see why the trend of moving down a column, okay, adding energy levels, is a far more important determinant of size than is moving across left to right. Because moving across makes a slight change just based on how tightly packed the electrons are. Okay? So I really don't even want you to memorize this. Okay? I don't care if you have that memorized. What I care about is you can explain the trend to me. Because if you can explain the trend to me, then you can go back and write out the pattern on your own. Okay, so that's the basic trend for atomic radius across the periodic table. So I could go back and use that now. I could say, which is larger, potassium or cesium? So let me write these out. So I want to know which is larger. K or CS. And then I could say why. So potassium versus cesium. Cesium is significantly larger because cesium has more energy levels. Okay? So obviously you would want to write that in better terms, but I'll kind of abbreviate that there. So then I could ask you, we'll say aluminum or silicon. Okay, so which is larger, aluminum or silicon? So in this case, aluminum is going to be larger. Okay, and the why is because silicon has a greater nuclear charge, which pulls electrons in closer. Okay, so if it pulls electrons in closer, that means the atom is smaller. Let's look at one more. Let's look at silicon versus gallium. Okay, so here we have an issue. You're moving up and down and left and right. But we know that the pattern as you move down the table is far more important because we add more energy levels. So gallium is larger here. And I could write that out in words because gallium has more energy levels, and the addition of energy levels is more important than the change in nuclear charge there. Okay, so we're mostly concerned when we move up and down and left to right in the up and down movement that has to do with the number of energy levels.